How do you actually measure whether an AI agent can handle complex, multi-step industrial tasks? Leaderboards promise an answer, but they often measure prompt engineering, not robust reasoning. The CODS 2025 ASSETOPSBENCH challenge was designed to test exactly that. Long horizon, privacy-preserving, multi-agent workflows for physical asset operations. But the real story isn't who won. It's what the competition's infrastructure, scoring design, and submission patterns reveal about the current state of agentic evaluation. Let's break down the architecture. The challenge split participants into two isolated tracks. Track 1 froze the execution environment and asked teams to improve the planning pipeline. Participants edited prompt construction and agent metadata to generate higher quality directed acyclic graphs, or DAGs, routing tasks across 4 domain-specific agents: IoT telemetry, failure mode and sensor relation, time series forecasting, and work order generation. Track 2 froze the plan and asked teams to improve the executor. Here, participants could replace the baseline sequential workflow with a dynamic workflow supporting parallel execution, cross-task context aggregation, and fault-tolerant fallback logic. Both tracks ran on a fixed LLaMA 370B model, inside a Dockerized environment to guarantee identical evaluation conditions. The scoring formula combined public and hidden components. Each track score was a weighted sum of public performance, private hidden performance, and a semantic match signal, then aggregated into a final ranking with 60% weight on execution and 40% on planning. On paper, this isolates capability. In practice, it exposed 3 critical evaluation failures. First, the public leaderboard saturated quickly and lost discriminative power. In the planning track, 4 teams hit the maximum public score of 72.73%. The binary per scenario grading created a discrete score grid where incremental prompt tweaks couldn't push teams past the ceiling. More importantly, public execution scores showed 0 predictive value for hidden performance. The Spearman rank correlation between public and private execution scores was negative 13%, with a p-value of 0.71. That's statistically indistinguishable from noise. Teams optimizing for the public signal were essentially gambling on scenario, phrasing, rather than building robust reasoning pipelines. The hidden phase didn't just verify results. It revealed that the public execution track was measuring surface compliance, not generalization. Second, the scoring formula contained a numerical scale mismatch that quietly distorted rankings. The semantic match component, tau, was calculated on a 0 to 1 scale, while the public and private scores operated on 0 to 100. This meant the 10% nominal weight of the semantic match term contributed at most 0.05 composite points. It was numerically inert. When we rescaled the match term to percentage units, or adjusted the execution to planning weight ratio, the top 2 teams swapped positions in over 56% of tested configurations. The official ranking wasn't a stable reflection of agent quality. It was a fragile artifact of 2 simultaneous, uncalibrated design choices. Future benchmarks must normalize all composite components to a common scale before aggregation, or explicitly report robustness sweeps alongside final standings. Third, the code-level analysis reveals what actually wins these competitions. We clustered 331 accessible source artifacts using HDBSCAN, a density-based algorithm that identifies clusters without forcing a predefined number of groups. The results showed a sharp asymmetry. Planning submissions scattered across 7 loosely connected clusters, with 32% labeled as noise. Execution submissions collapsed into 3 tight clusters with only 2% noise. The top execution systems weren't architectural innovators. They were guardrail engineers. The dominant patterns were soft validation fallbacks that catch type errors and proceed with partial results, external LLM refinement loops, keyword overlap executors, and forbidden word filters. These teams improved response selection, cleanup, context control, and fault recovery rather than introducing novel agent topologies. Planning was commoditized by scaffold elaboration. Execution was structured around defensive orchestration. This brings us to the compute illusion. Token consumption is often used as a proxy for task difficulty or agent complexity, but the trajectory data tells a different story. Work order scenarios consumed 244,000 tokens on average, but exhibited the lowest strategy variance and highest phase stability, meaning their cost was task-intrinsic and not gameable. Time series forecasting scenarios consumed only 35,000 tokens, but showed the highest coefficient of variation, making them highly prompt-sensitive. End-to-end multi-agent scenarios sat in the middle for tokens, but demanded the highest wall clock duration, exposing an orchestration latency cost that token counts completely miss. Single-agent executions actually consumed nearly twice the tokens of multi-agent executions, because the single-agent pool was dominated by heavy work order decision support queries. Success correlated negatively with token usage, execution length, and tool entropy. The evaluation agent did not reward verbosity or over-engineered trajectories. It rewarded concise, controlled execution. Failure mode analysis confirms that hallucination is not an isolated bug. It's a leading indicator. Across all 22 scenarios, the Pearson correlation between hallucination rate and overall task quality was negative 93%. When agents hallucinate, they're almost always failing on data retrieval, result verification, or sequence correctness as well. The consistent capability ceiling across both development and evaluation phases was work order reasoning. Multi-year event aggregation, constraint-based bundling, and temporal maintenance scheduling broke agents repeatedly. This isn't a benchmark artifact. It's a genuine gap in long-horizon reasoning over historical maintenance records. So what do we do with this? The competition wasn't just a ranking mechanism. It was a stress test for evaluation design. It surfaces 4 concrete prescriptions for future agentic benchmarks. First, isolate capability dimensions across tracks and evaluate them independently from the start, rather than using the public phase as a proxy for hidden robustness. Second, surface skill-aware subscores. Aggregate task completion masks the difference between an agent that hallucinates to finish and one that fails gracefully. Third, ensure scoring components are numerically commensurate. A mismatched scale can silently reorder rankings and reward optimization strategies that don't generalize. Fourth, treat team metadata, container digests, and versioned code as core deliverables. Strategy attribution requires ground truth access to implementation patterns, not just leaderboard positions. The gap between laboratory agent capabilities and industrial deployment isn't just about model size or prompt design. It's about how we measure progress. If our benchmarks reward prompt surface elaboration, ignore metric scale alignment, and treat token count as a difficulty proxy, we'll keep optimizing for the wrong signals. The CODS 2025 challenge proves that rigorous, transparent evaluation infrastructure is the actual bottleneck. When we fix the measurement, the engineering follows.